Welcome to the penultimate video on our series of the S-block elements and their compounds, and this time we'll be focusing on solubility. So we'll start by looking at the solubility of the group 1 and 2 compounds in general and the trends in the groups, and then we'll look at a bit more in detail why these trends come about, what factors influence solubility, and a look at the thermodynamics behind it also. We'll start by looking at the solubility of group 1 compounds. In general, most group 1 salts are soluble in water. We'll go into it a bit more in detail in the later slides, but the idea behind solubility is that it's a competition between the lattice energy of the ionic solid and the energy of each individual ion being hydrated. Now, as I said, we'll look at this in thermodynamic terms in a few slides' time. But when we think of the lattice energy of group 1 salts, it's much lower than those of group 2, for example, because the charges are only 1 plus, 1 minus. So there are weaker interactions, therefore lower lattice energy. So in general, most group 1 salts are fairly soluble in water. There are, however, still trends. So those containing large anions, so if we're looking at things like chloride, bromide, iodide anions, and also some of the large anions, like the oxoanions we were looking at in the last video, the carbonates and nitrates, their solubility decreases down a group. So we can see in this periodic table here that shows the ionic radii. With large anions, as you descend the group, and therefore we're looking at larger cations, the solubility decreases. For those with small anions, so we're looking at things like the fluoride anion and the OH, the hydroxide anion, the solubility increases down the group. So this time rubidium, cesium are the most soluble. So we can see here it's almost a mismatch between the ionic sizes. So for those with large anions, the smaller cations at the top of the group are more soluble, and for small anions, the larger cations at the bottom of the group are more soluble. Now with group 2, we have a similar trend, but in general, the salts are less soluble. This reflects what I said at the beginning of the last slide when we look at the lattice energy. So group 2 ionic salts have cations in the 2 plus and anions they're attracting 2 minus or 2 negatively charged anions to compensate. Therefore, there are stronger forces in the lattice because of these larger charges and a stronger lattice energy. So in general, the solubility of group 2 salts is lower. However, the trends still apply. So we can see here, if we're looking at small anions, the small cation salts are less soluble than the large cation salts, and the opposite is true for large anions. So a large anion with a small cation is more soluble than a large anion with a large cation. So now let's look at why this is. So I said at the beginning that whether an ionic compound is soluble is a competition between the lattice energy and the energies of hydration of the ions into solution. So we've got the definition of what the energy change of hydration is here as well. So this is the Gibbs energy change for the process, which is A+, which doesn't have to be a cation, it's also could be an anion as well. So just an ion of any type in the gas phase to that in aqueous phase under standard conditions. And in the same way that we can work out whether an ionic compound will be stable with respect to the elements by looking at Born-Haber cycle, we can do the same thing here with solvation. So we take an ionic structure and turn it into aqueous ions. This is the energy of solvation. So let's write this here and we can get the equation as well. And then we can do exactly the same as we did last time with Hess's law, following the individual steps. So then we've also got the lattice energy, delta lat G. This is a positive value, and that's because this time we actually are following the definition from an ionic solid into gaseous ionic atoms. So delta sol G equals delta lat G plus the hydration energies that we've just seen the definition of. Plus there we go. Now, one thing you'll notice about this Born-Haber cycle is that everything is in delta G rather than delta H as we've been used to. Now, what we've been using delta H up to now is that if the value of delta G is very large, then we can safely ignore, or usually safely ignore the T delta S term, and the value of the enthalpy change relates or corresponds very well to the value of Gibbs free energy change. So you should know that Gibbs free energy change, if it's below zero, a process will occur spontaneously. If it's above zero, it won't occur. So when we've been looking at the formation of ionic compounds, we've just been using the enthalpy changes in these Born-Haber cycles, and we've sometimes seen, like in the case for the sodium dichloride, NaCl2, in one of the questions in the last video, we got a really large positive value of delta H. Now, this will correspond to a very large positive value of delta G as well, and therefore we can say that this process isn't going to occur. However, when we're looking at solvation, delta G of solvation, which is telling us whether something will be soluble or not, is a very small value, much smaller than the energies of formation that we were looking at before. And when delta G is small, we've got to take into account this T delta S term. Therefore, with each of these steps, we're looking at the Gibbs free energy rather than the enthalpy. It's also important to know that I said delta G of solvation is very small. These other values are all very large though. So delta G of the lattice is very large and positive, much like the enthalpy of formation that we've been, the lattice enthalpy we've been looking at for the last few lectures. So delta G lat is large and positive, and delta G of hydration of both of the ions is also a large value, but this time negative. So then we've got even though these are, you have to plus each term, the value of them will be negative. So we've got a large positive term minus two large negative terms, and that ends up giving us like quite a small value of delta G. And what this means is that a change in any one of these three terms can have quite a big effect on whether a compound goes from soluble to insoluble. Now, the video link I've got down here is to the author of the book again, explaining all this and working through an example, and he does it really well, so I'd suggest watching that, and I've put the link in the YouTube video as well. But in the next slide, we'll look at what affects these three terms. Now, I said that because delta G sol is small and the other three terms are very large, if we make a small change to one of these three terms here, it has a big effect on whether it's soluble or not. So let's just quickly look at some of the ways these numbers change, like what affects them, what makes them larger or smaller. So we'll start with we'll split it down the middle here. So we've got the lattice energy on the left and the things that affect it, and the hydration energies on the right hand side of the slide. So the lattice free energy is very much related to the lattice enthalpy, which is calculated through the Kapuscinski equation. So if we just write that down quickly, because this will help us see what affects it. So we've already seen that solubility, the trends in solubility are whether the cations and anions are large or small. So let's see how that affects this term. So if you've got large ions, then this term on the bottom, R plus R minus, will be really big, and therefore we're dividing by a very large number. So this leads to a small, small delta G lat. And if and then the opposite is obviously true. Now, if this ionic radii are small, we see we're dividing by a small term on the bottom. So then we end up with a large lattice energy. So now looking at the energy of hydration, there's not really an equation for this. It is more of a rule, is that large ions have a smaller hydration energy, and small ions have a large hydration energy. So therefore we can see already that the size is making a big difference to each of these three terms that really affect whether it's soluble or not. So on the next slide I'll go through each of the cases, large, 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 small, small, large and small, small, and see which of the terms is really driving the process of solubility. And I've got this table here then to summarise the effects of all of these. So we've got the points that are important so far at the top. The magnitudes of lattice and hydration energies are all large. Remember, lattice is positive and hydration energies are negative, whereas the solvation energy is small. And this means small changes in any of these three terms cause a change from soluble to non-soluble. So if you take the case of small cation and small anion, you remember from the trends that this leads to an insoluble compound. And this is because the delta G of the lattice is going to be very high. If you remember back to the last slide, we're dividing by a small number in the Kapustynski equation. So we've got a very high positive value and two high but not so high negative values. And this means that delta G of this solvation will be positive and therefore the compound's insoluble. However, if we take a small cation and combine it with a large anion, we then see that the delta G of hydration of the cation is what's dominating. So the lattice energy isn't quite as high as it was before because we've got a larger number on the bottom of the equation. The anion has low hydration. As I said on the last slide, large ions have low hydration energies. But the cation is small, and this is then the dominating factor. And this can cause the solubility energy to be small, and therefore can be negative even, and therefore the compound is soluble. It's very similar again with a large cation, small anion case. It's soluble, and delta G sol is negative. But this time it's the anion hydration energy that's very high and the term that's dominating because this is the smaller ion. And finally, the large cation and large anion, all of the values are low. So we know that large ions have low hydration energies. If you've got two large ions, the term on the bottom of the Kapustynski equation is very large, leading to a low lattice energy. But in this case, even though they're all low, it's the lattice energy that dominates it. That's big enough that the hydration energies don't drag a delta G sol as to a negative number, and therefore the compound's insoluble. So the main things to take back are that if the cation and anion are the same size, it's likely to be insoluble. If there's a mismatch in size between the cation and anion, it's likely to be soluble. And that salts of group 1 metals, remember, are in general more soluble than salts of group 2.